Black holes are famous for being black, but here's the twist: they aren't truly black. In 1974, Stephen Hawking showed that even a black hole should glow slowly evaporating away. The misconception is that black hole equals perfect sink, like an endless drain that never lets anything out. But physics says the opposite. The horizon behaves like a thermal machine, and over time the machine leaks until the black hole disappears. So ask yourself this: if black holes radiate, what does that mean for the fate of information? And why would quantum rules near the edge of space-time trigger a runaway event so dramatic it ends with the collapse of the very idea that nothing can escape? This matters right now because Hawking's calculation connects the biggest scales, gravity and horizons, to the smallest quantum fluctuations. It's not just a weird prediction. It's one of the deepest stress tests we have for our understanding of reality. Before Hawking, the prevailing picture came from Einstein's general relativity. A black hole forms when mass collapses enough to warp space-time so strongly that a boundary forms, the event horizon. Inside it, paths forward inevitably point deeper in. For decades, the standard expectation was, if light can't escape, then neither can anything else. Quantum mechanics didn't change that intuition at the horizon, because quantum fields were usually treated in ways that suggested nothing emerges from the trapped region. Meanwhile, physicists wrestled with a separate puzzle: entropy. In everyday life, entropy measures disorder and determines which processes are irreversible. In thermodynamics, information gets lost into heat. So the big question before Hawking was whether black holes obey any thermodynamic law at all, whether horizons have entropy, and whether they have temperature. Hawking's argument begins with a simple but revolutionary idea: the vacuum isn't empty. In quantum field theory, even nothing is restless. Particle-antiparticle pairs pop into existence and annihilate almost immediately, fluctuating everywhere. Now imagine placing this quantum foam near an event horizon. The pairs can be created in such a way that one particle falls behind the horizon while its partner escapes to the outside world. To a distant observer, the escaping partner looks real, like radiation. The escaping energy doesn't come from stuff inside the black hole, violating classical rules. Instead, it comes from the fact that the black hole's gravitational field effectively gives the quantum fluctuations a chance to separate into observable outcomes. That separation is biased by the horizon geometry, which makes the escaping spectrum thermal. Here's the deeper mechanism. Hawking used quantum theory in curved spacetime. Curvature changes what particle even means, depending on the observer. Near the horizon, the mismatch between the vacuum state defined at different times leads to a consistent prediction. The black hole emits radiation with a temperature inversely proportional to its mass. In formula terms, hotter for smaller black holes, colder for larger ones. That sets up the runaway. As the black hole emits, it loses mass. Losing mass raises its temperature. Higher temperature means more radiation power. More radiation power means faster mass loss. It's a feedback loop. Evaporation accelerates as the black hole shrinks until the Sivers-Sadikal approximation eventually breaks and a final, uncertain phase occurs. To make the runaway intuitive, picture the black hole as a thermostat controlled by its own size. The smaller it becomes, the hotter it runs, and the hotter it runs, the faster it sheds mass. The horizon isn't just a one-way gate. It's an active boundary where quantum effects turn geometry into thermodynamics. And thermodynamics brings entropy into the story. If radiation carries entropy outward, then the black hole must have entropy associated with its horizon area so that total entropy doesn't decrease. That's where the phrase black hole entropy stops being metaphor and becomes a requirement. The horizon behaves like it stores information about the gravitational microstates, even if we can't directly identify them. The broader implications are enormous. First, Hawking radiation ties black holes to ordinary thermodynamic laws, suggesting that gravity has an accounting system for entropy. Second, it creates the information paradox. If the black hole evaporates completely, what happens to anything that fell in? Particles, correlations, the detailed quantum state. Hawking's original view implied information might be destroyed, leaving behind only thermal radiation, which seems to erase fine-grained information. That clashes with the quantum principle that evolution should preserve information. Third, the runaway evaporation means black holes are not eternal. The universe won't just host static holes. It will eventually process them away, converting gravitational mass into radiation and entropy. In modern physics, this becomes a roadmap to deeper theory. The holographic principle and developments in quantum gravity aim to reconcile Hawking's theoretical results with unitary quantum mechanics, implying that the information is not lost but encoded in subtle correlations within the radiation. That reconciliation is still an active frontier, but the existence of Hawking radiation itself is a powerful compass. It says any successful theory of quantum gravity must reproduce thermal emission and the entropy behavior of horizons. It also motivates how we think about spacetime and measurement. The event horizon is no longer merely a geometric boundary. It's a physical interface where quantum fields become thermodynamic systems. That's a shift in worldview. Less spacetime is just a stage. More spacetime is an active participant in quantum processes. So, where does this leave us? The journey starts with a paradoxical question. Can something that traps everything still radiate? Hawking answered by combining the horizon geometry of general relativity with the restless vacuum of quantum field theory. The result is a thermal glow whose power accelerates as the black hole loses mass, pushing the system toward complete evaporation in the cephalrachical picture. In the process, black holes gain entropy, follow laws that resemble thermodynamics, and trigger a deep conflict between classical intuition and quantum information. That conflict is the reason the story matters beyond black holes themselves. It's a litmus test for our deepest theories. And the mic drop is this: the most extreme objects in the universe aren't just swallowing matter. They're proving that horizons have temperature, entropy, and a quantum life of their own. If you want more like how the information paradox is being attacked from every angle, subscribe for the next one.